Hi, Tansu. Did you want to test your audio visual before we get started? We have about a minute.
Sure, I could. I mean, I just gave another talk, so I'm sure.
Okay. Only if you need to. I can hear and see you, so.
Hey everybody, Brickleg.
This may be a weird thing to check. Is my background the right way around? I like turned it on and it looked like it was the wrong way around.
Yeah, you're good.
Thank you.
Sometimes it'll flip your camera.
Yeah, I was a bit confused because when I first put it up, it was flipped and then I changed. Thank you.
Okay, so we are at the hour mark. Thanks everybody for coming back for the afternoon session for stellar astrophysics. This is the splinter session, or the parallel session rather. We have 4 talks today. They are 12 plus 3 minutes. We would like for you to ask questions in the Stellar Astrophysics channel for this section, and I will keep an eye on that Slack channel and ask your questions for you to the speakers. So without further ado, let's have our first speaker. This is Marc, and he's going to be talking about some galactic archaeology.
All right, can everyone see my slides and hear me?
Yep, I can see and hear you. Take it away.
All right, thank you for the introduction. My name is Marc. I am a Hubble Fellow at the University of Hawaii, and today I'm going to give everyone a quick look at near-all-sky galactic archaeology with TESS. Now, TESS allows us to listen to the songs of stars from nearly all directions in the sky, and this is crucial if we want to probe stellar populations around the Milky Way in great detail. And by listening to the songs of stars, of course, I mean that we use the asteroseismology of solar-like stars. Such stars, including that of our sun, have convective outer envelopes that stochastically excite acoustic standing waves that propagate throughout the stellar interior. These standing waves cause parts of the stellar surface to expand and contract, resulting in changes to the luminosity of the star as a function of time. Now, missions like Kepler and TESS measure these changes in luminosity as light curves, as we know. And in seismology, we take the Fourier transform of these light curves to get power spectra. So the power spectrum of a typical solar-like star would look something like this, where you have signals from rotation and activity at lower frequencies. But what we're looking for that corresponds to the global oscillations is this power excess that's sitting on top of all the other contributions. Zooming in, we see that it comprises an envelope that modulates a set of regularly spaced peaks. Now, I like to think of these peaks as musical notes that are being played by the star, but these are, of course, the oscillation modes. Each mode tells you something about the interior sound speed of the star and therefore the stellar structure. Now, in my talk, I want to focus on a broader seismic measurement, what we call the frequency at maximum power, or Umax. So this is approximately the center of the oscillation power envelope. So this measurement defines a typical oscillation timescale for the star, and is fundamentally linked to the star's mass, radius, and temperature. And in seismology, we have here a powerful relation shown here on the right, what we call a scaling relation, which says if we could measure Umax for any solar-like star, or rather star showing solar-like oscillations, then that star's mass, radius, and temperature would be scaled versions of the same quantities that we can measure from the sun. And this gives us a really powerful way to constrain the fundamental parameters of any star showing solar-like oscillations. So to put this more concretely, let's think about the H-R diagram. Stars like our sun live on the main sequence. They have smaller radii and therefore they oscillate at higher frequencies. But as the star evolves into a red giant, its temperature cools down and its radius increases. So the oscillation frequencies shift to lower values. Now, just like you would compare a clarinet to a tuba, the larger instrument plays music at lower pitches. And in our analysis, we want to focus more on the giants because it turns out that the larger instrument here also plays music louder. What I mean, of course, is that the oscillation amplitudes for giants are much larger compared to stars on the main sequence. And this makes it easier for us to identify the presence of oscillations in red giants. So the oscillation amplitudes scale with the radius of the star. And this is important when we want to probe farther out into the galaxy, because stars that are farther away would have more faint magnitudes. And this would mean that the white noise levels in the power spectra will rise. So crucially, what we want to do is to identify the presence of the oscillation power excess in each red giant power spectrum. Thankfully, we have algorithms that do this automatically for us. We have machine learning algorithms where we can feed in images of power spectra, and the algorithm will tell us whether or not oscillations are present. And if they are present, it will also tell us at what frequency the oscillations can be found. So essentially predicting the value of Umax. So we want to take this tool and apply it to all the light curves that we could find across TESS. Now there's a reason why we call this a quick look analysis. A second reason rather, it's because we use data from MIT's quick look pipeline, which has given us a staggering 24 million light curve data set down to a TESS magnitude of 13.5. It's really not something that you want to go through one by one. But nonetheless, we've applied our algorithm to all the light curves in this data set. And at first glance, we seem to pick up giant oscillations in just about everything. Not just giants, but also dwarfs on the main sequence, which is a bit strange, but it turns out that a lot of these dwarf stars showing giant oscillations are actually fainter targets neighboring giant stars. So the flux from the giant star, from the bright giant star, is blending into the pixel aperture of the fainter target. And this is not ideal because we want to study genuine giants and not dwarf stars masquerading as giants. So we impose another constraint. The star shows giant oscillations, but it also must have a temperature and a radius of a giant. And here is where we appeal to other all-sky surveys, Gaia and 2MASS, to help us with this identification. Gaia gives us parallaxes from which we can compute distances. 2MASS gives us JHK magnitudes from which we can derive a color. And these magnitudes, when combined with distances, bolometric corrections, and extinction maps, gives us a luminosity. So we have temperature, we have luminosity, we can compute a radius. So putting it all together, we have three constraints for our selection. The star must show giant oscillations, it must have a temperature and a radius of a giant, and finally, it must be sufficiently bright for us to even expect there to be oscillations in the first place. So putting it all together, we have this distribution shown here in red. And as you can see, we are picking out only the giants on the HR diagram. Now, if we look at this distribution in frequency magnitude space, we see that at brighter magnitudes, we get a whole range of frequencies, but past the TESS magnitude of 10, we start to lose high frequency oscillators. Now remember, these high frequency oscillators are also those that oscillate with the lowest amplitudes. So this is the region at which the white noise levels in the power spectra really start to ramp up and we don't see these oscillations. What's unexpected, however, is that we lose these faint and luminous giants. And we believe this to be a current limitation of our machine learning algorithm that we are trying to overcome. But nonetheless, just by looking at all the stars in red, we have a total of 158,000 targets for which we are confident shows giant oscillations and are actually giants. We consider this to be a conservative first estimate to the total number of oscillating giants that we could find across the entirety of TESS. But nonetheless, it is the largest sample of oscillating giants that we have to date. Now, what we can do is go back to the Umax scaling relation and ask, we have Umax, we have radius, we have temperature. What is the distribution of masses across the entire sky? Here is where I present to you the first ever near all sky seismic mass map of the galaxy. At the top, you have the optical image from TESS, and on the bottom, you have a near all sky concert. Now let's unpack what we're seeing here. The brighter parts of the map correspond to more massive regions. So what this is telling us is that the galactic plane in particular, which is the equator in this map, typically has more massive stars compared to regions that are farther away from the plane. Now, to make sense of this, remember that the masses of stars are often anti-correlated with their ages. So the more massive a star is, the less likely it is to live very long. And conversely, some of the least massive stars tend to live the longest. So going back to the map, this tells us that the galactic plane is home to a lot of young stars compared to regions that are farther away from the plane. And this makes sense because remember, the galactic plane is home to the spiral arms of the Milky Way, and is rich in gas and dust, materials needed to continuously make new stars. So the plane of the galaxy is a region of active star formation, and we should indeed expect there to be a lot more young stars here. Now, if we look at the range of masses as a function of altitude, we find that close to the galactic plane, we have a broad range of masses. But as we move to higher altitudes from the plane, this mass range starts to shrink up to the very top, where we have only a small mass range of low mass stars. And this is the known vertical mass gradient of the Milky Way disk, except now that we have a lot more stars to probe this structure in greater detail. Another way of looking at our sample is through the kinematics. Now, populations in the Milky Way halo can often be disentangled kinematically into those in the disk and those in the halo. Here we show a tumor diagram where we find that most of our sample lies within the disk of the Milky Way, at least kinematically. And this includes a lot of more massive stars. And this agrees with our understanding that the disk is home to a lot more young stars compared to the halo. Now, we find a few hundred stars in our sample with halo-like kinematics, and these correspond to many low-mass stars, which agrees with our understanding that the halo stars are typically quite old. And so we also look at the velocity dispersion of our sample, of stars in our sample, where it is accepted that typically as stars age, they tend to have larger radial and vertical velocity dispersions. By plotting masses as a function of velocity dispersions, we do see that indeed some of the least massive stars in our sample have the highest dispersions, which agrees with kinematic models of the Milky Way. So finally, we validate our results by looking at chemical patterns, where we appeal to the well-known alpha abundance versus metallicity plot, where the idea here is that within the solar neighborhood, stars that are young would have a very small scatter in their alpha abundances. It would be about solar, whereas the older stars in the solar neighborhood would have a much larger scatter in their alpha abundances. So we plot our giants as a function of mass following this pattern, and we do see that the high mass stars in our sample, or the youngest, have abundances of alpha elements near solar as expected, whereas the low mass stars have a large scatter in their alpha abundances, which agrees with previous studies. And this is an important astrophysical validation of the seismology that we set out to do. So I'd like to wrap this up and say that all of these results are just based with 1 month of seismology on TESS data. We are probing a region up to 1 kiloparsec around the sun, but this is just the beginning. Imagine what we can do with more observations from TESS. We can probe even farther, and the precision of our seismology will only get better. So here is where I'll leave you with my takeaways. We have presented the first near all-sky seismic mass map of the galaxy. We have close to 160,000 oscillating giants across the sky. And the term bright is something that we normally use to describe the stars observed by TESS. But I think the term bright can also be used here to describe the future of galactic archaeology with TESS. Thank you very much for your time.
Thanks, Marc. Great talk. So we have questions rolling in. The first is from Zach Clater, and he asks, do you have any hunches about what the source of the limitation to the machine learning algorithm might be regarding the low frequency objects at faint TMAG? Yeah.
Yes, I do have a hunch about it.
So, that was my question too.
Okay, yeah, it's an important question that we really should revisit at some point, but I'm just going to go back to the power spectra just to get an idea of what the network looks at. So scrolling. Okay, so we move to this plot. Hopefully you also can see it. This is the power spectra as a function of magnitude. So the idea is that the network, the algorithm here, what it uses to pick out oscillations, especially for the low Newmax stars, is the presence of granulation, so the presence of this slope. Now for fainter stars, the white noise levels start to ramp up. So the white noise is basically just a flat line. And when that happens, when the white noise levels start to ramp up, you lose a lot of your signature of that granulation curve. And it makes it really difficult to pick out these very low frequency oscillations when you have no signal of granulation whatsoever. Even eyeballing it is actually quite difficult, I have to say.
Thanks. Next question from Monica Djokovic. Great talk. Does your sample include red clump stars?
Yeah, there's plenty of red clump stars in our sample. In fact, yeah, you can see here. Well, maybe this is a better one here. Yeah, plenty of red clump stars.
Excellent. Okay, I'm not seeing any more questions. And in the spirit of keeping us on time, let's thank Marc. And we'll get ready for our next speaker, which is going to be Ted Mackereth. And he's going to be talking again about galactic and stellar astrophysics in the TESS-CVZs.
Okay, am I unmuted? I think I am.
Yeah, I can see and hear you. You're good to go.
Great. Okay, so hi, my name is Ted Mackereth. I'm a postdoc at the University of Toronto, but the work I'm going to talk about today is stuff I did while I was a postdoc at the University of Birmingham with some of the fine folks that I've mentioned there who have really supported most of the stuff that I'm going to present in this talk today. So none of this would have been possible without all these people named here and all the other people who are on the paper that I'm talking about. And so I feel like my talk is a little bit of like an appendix to Marc's talk, since he's already done all this stuff all sky now. But this work we started back in 2019, actually, to make a first look at the TESS continuous viewing zone and see what we could do with seismology there. And this is all related to Andrea Miglio's ERC project, which is titled Astrochronometry, which aims to connect seismology with galactic archaeology studies. And that's where I'm going to make this disclaimer that I'm not actually a stellar astrophysicist, and I had never seen a light curve before I started my postdoc in Birmingham. So there are a lot of people at this conference that know a lot more about the stuff I'm going to talk about in this talk today. And really my goal as a galactic archaeologist was to kind of connect what the amazing work that everybody is doing with TESS and Kepler to get stellar ages, and use that to do interesting work on the history and of evolution and formation of the Milky Way. And so Sam Grunblatt already spoke about what galactic archaeology is, but essentially it's using the stars of the Milky Way as a kind of fossil record of galaxy formation. And then using things like seismology to get their ages, we can sort of really develop a chronological history of the Milky Way and use that to understand galaxies, and hopefully galaxies in general. And this idea of galactic archaeology always makes me think of this meme, which I thought was kind of funny. And so large astroseismic samples are already teaching us a lot about the Milky Way. So Marc showed this in his talk as well. This is work from Silva Aguirre using Kepler that measured ages for a large sample of stars within the Kepler field, which overlapped with apogee and therefore had element abundances. And this just shows age versus alpha to ion for a set of those stars. And one of the most interesting parts of this work and many others that have looked at Kepler ages was that we found this population of stars which are alpha enriched but mysteriously young. So we think actually that these stars are overmassive because they accreted extra mass while they were on the main sequence and then evolved to be red giants, and we now measure them to have a slightly higher mass than they should have, and therefore we infer that they have a younger age. But Victor's work also showed that there's this interesting distinction between the ages of the low and high alpha sequence. Some other work, just as another example, this recent paper by Andrea Miglio, which looked at the vertical velocity dispersion of stars as a function of age, again measured from Kepler light curves, using extra spectroscopic parameters from apogee, showed that there's this neat relationship between the age and velocity dispersion on the low alpha sequence. And then when you select stars in this high alpha sequence, which all appear to be much older and have a very consistent age, as Marc mentioned as well, you see that there's a kind of a break in this age velocity dispersion relationship, which is indicating that those stars probably had a slightly different history of dynamical heating, which is a kind of interesting result in telling us a little bit about the history of the Milky Way. Another really interesting part of astroseismic samples and the Milky Way is that people have now been able to use machine learning to derive data-driven models to get stellar ages for samples where we have crossover between spectroscopic data and astroseismic data, where we can take the astroseismic age constraints and sort of paint those onto the spectroscopic samples. And I think that's really where the future is brightest for doing for using astroseismology to do galactic archaeology, is actually using it as a kind of a ladder, if you like, and measuring ages and then painting those onto larger samples. And so Yeah, so I set about this project as a kind of coordinator, if you like, and I was really sort of tasked with going and looking at the TESS FFIs and seeing what we could do with seismology there and what constraints we could get on galactic archaeology based on a first look. And so the TESS FFI light curves, it seems, are just fine for seismology. Marc showed that there's plenty of information in those light curves. And so maybe TESS is secretly a stars mission, it turns out. So maybe we shouldn't let the exoplanetiers know too much about that. But this paper by Victor Silva Aguirre again showed that with single sector TESS data, you can easily measure oscillation modes in red giants in single sectors of TESS. And he showed that really you can actually also detect the individual radial mode frequencies as well, very neatly. And so we went to look at stars in the CVZ to see if we could get longer light curves where we might be able to probe deeper down the red giant branch in those higher frequency oscillation range. And so I sent a bunch of stars to Mimo Nardiello, who's actually an exoplanetier, it turns out, and he was able to extract light curves for a set of stars in the CVZs for us. Using his exoplanet light curve extraction regime. And he was then also able to do some corrections to those light curves for us. And actually, it turns out that was the most tricky part, right? So extracting the light curves from FFIs is fine, but then actually correcting those, you can see here is just one example where we've taken an uncorrected light curve of in sector 1, which had this dropout of a data loss at the latest section of that light curve. He was able to correct those and provide these really nice light curves. And then actually stitching those together as well, it was a mammoth task, and that's something that was a lot of work was done kind of for me in this project. And so my role was really just to make the selections of stars and choose something that was maybe astrophysically interesting. So we were able to select all of these bright giants in the southern CVZ. We selected 15,000 giants from Gaia with a G-band magnitude of less than 11. So these are really bright, and with parallax uncertainties less than 10%, because we wanted to see if luminosity measurements were able to help us increase the precision of our measurements later on. And I'll talk about that a little bit. So we selected stars roughly in the region of the CVZ, and we selected 15,000 stars, but then we actually found that only 3,000 of those actually had 13 sectors of data when you go to these bright magnitudes. And so the continuous viewing zone is not necessarily continuous, but I think if you went slightly deeper in terms of magnitude, you would find that there was many more giant stars that had more sectors of data. And of course, with the extended mission, we might see some more sectors being added to those stars as well. And so we took those giants and we ran them through a selection of pipelines. We looked at 3 pipelines, the pipeline from Yvonne Ellsworth, Benoit Mosser's group's pipeline, and Savita Mathur and Rafa Garcia ran it through their pipeline as well, in order to try and detect those global parameters of the power spectra that Marc mentioned. And it seems that the yields that we get from the stars are actually pretty good. So I showed there a color magnitude diagram where we showed that this dashed line kind of shows where we predicted that we might be able to make those detections of those oscillation modes that Marc showed in his talk. And we found that when we ran through these automated pipelines, which were really kind of trained and developed for Kepler, we were able to recover pretty good exactly what we expected to get. So we found, so these contours here just show us the rough regions where we were able to detect oscillations with these 3 pipelines. And then you can kind of see that we kind of dropped off in terms of the yield that we were getting at this bright end. And a lot of the reason for that was already alluded to in Marc's talk as well. But what we were finding was that when you compared yields as a function of the number of sectors, the absolute magnitude, and the color of the stars, if you made a model that didn't account for that dilution effect, or that photo bombing by bright stars, if you like, you saw that the yields you expected were much greater than the actual yields that you got if you included the effect of this dilution. So by accounting for the fact that you've got many faint stars and also a few bright stars in the pixels where you're actually detecting these giants, we were able to actually recover roughly the yields we were expecting. So the yields are looking pretty good actually. So we weren't really missing out on a lot of detections there. And then, as I mentioned before, these pipelines were actually really developed and trained for TESS. And so a lot of the work that we put into this paper was just tweaking those pipelines to actually work for the FFI data. And so all of these different groups, Yvonne, Benoit, and Savita's groups, were able to go and take their pipelines and kind of make sure that they were getting the optimal number of detections. And these plots just kind of compare the detections we were getting from the other pipelines versus the reference pipeline, in this case the BHM one, which is Yvonne Ellsworth's pipeline. And really what we were finding was that between pipelines, the consistency was at roughly the level of Kepler, slightly worse perhaps. So Kepler was about 2 to 3% consistency between individual pipelines for determining those global parameters, and we were getting something closer to sort of 3 to 10% in the worst case scenarios. And of course, there are still a lot of cases where the detections we were getting in one pipeline were completely different to the others. And a lot of that are for reasons that Marc mentioned, for this, in the sense that you kind of get a lot of noise in these stars which have oscillations at higher frequencies. And so in the end, we were able to get a sample of stars, 5,574 stars with consistent detections across 3 of the pipelines that we used. And then we were able to actually find about 1,500 of those, which had 13 sectors of data and were consistent within 1 sigma between all of those pipelines. This makes a nice data set where we've been able to kind of cross-check between many pipelines that we're getting consistent detections. And for example, you might then use this sample to do sort of machine learning techniques, which are similar to those that Marc mentioned in his talk. And so a great thing about TESS is it actually ends up to be sort of less biased than Kepler when it comes to interesting evolutionary stages on the giant branch. So I think May Peterson talked about this in her talk as well, but there's lots of interesting stellar evolutionary stages in TESS because it's kind of unbiased as to where it's looking in the sky. And so with the FFI, you can basically pick any star from Gaia and go and see if you detect oscillations there. And in our sample, we found a few astrophysically interesting evolutionary stages. And this just kind of shows in the mass versus absolute K-band magnitude plane, roughly where in terms of the isochrones we expect these evolutionary stages to be. And then I've kind of selected just example stars in each of those interesting regimes. So here you see an RGB star in this lower panel, a common Guardian red clump star in this central panel, which has oscillations at a slightly lower frequency. And then as well, most interestingly, perhaps in the context of stellar astrophysics, we were able to detect many of these sort of early AGB stars, we think. And these have really interesting spectra, which are very rich in features. And there's a whole treasure trove of things to go and understand there. And I'm going to leave that to the stellar astrophysicists, because that's where I kind of get off the train. But yeah, we were able to derive these masses using seismology and sky mapper stellar parameters. And we think the uncertainties were pretty good. What it turns out is that actually including the Gaia luminosities as a constraint in our fits, so we use the param code to fit the seismology and the stellar parameters against a grid of parsec stellar evolution models. Including the Gaia luminosities really improves the precision that you can measure these things to. So I'm just showing here mass and age as measured from param. And in the dashed lines, I'm showing if you don't include the luminosity, this is the kind of distribution of fractional uncertainties that you get. And you can see it goes, for ages, it goes all the way from pretty good to absolutely terrible, almost 100% uncertainty in the age. When you include that Gaia luminosity, you see that you really tighten up the uncertainties. And for example, the ages peak at around 30% uncertainties, and the masses go to about 10%, which is comparable to what you get from Kepler if you don't include the Gaia luminosities. And a lot of the reason for that is, I think, similar to what Marc was saying, is that you kind of see, you're kind of be able to determine between what's a giant and what's a dwarf and what is actually a kind of false positive by using these Gaia luminosities. And so that really improves your ability to actually do interesting science with this data. And so the other great thing about the TESS-CVZ giants is, as you can just go and select any of the stars in the CVZ, and they're now targeted by many of these spectroscopic surveys, for example, like Apogee. So back when we wrote this paper, we were only able to access Apogee DR16, but now there's plenty more Apogee data on the way for the CVZ as well. And we found 300 stars in common between Apogee and our CVZ giant sample where we can measure ages. And you can see that we were able to recover a lot of the interesting trends, for example, in the magnesium over iron to iron plane, where you see the low and high alpha populations of stars, which I spoke about before. You can see that we recovered roughly the age of that high alpha sequence as being very old and kind of consistent with a single age, except for some outliers, which are these young alpha rich stars. And in the low alpha population, we see this large spread in ages from the ages we were able to derive when we included the Apogee spectroscopic parameters as well. And so eventually, I think the CVZ data will make an excellent training set for these machine learning applications, because you can take those 12 sector data stars, measure their ages and things very precisely, and then paint that over onto that full sky sample. Of course, the radial extent of stars in the southern continuous viewing zone is kind of limited, but what we were able to see was that actually when you just select stars in a small region of space, if you look at where those stars first started in the galaxy, so by integrating their orbits backwards in time to their ages, we're able to see that actually by just sampling that small range of radii, today you're actually seeing a huge dynamical sampling of the disk. And so I think this is kind of an interesting data set for looking at things like radial migration of stars within the disk of the galaxy. So on the plot there, I'm just showing the kind of birth positions, if you like, of the stars from the southern CVZ. Of course, this is all kind of relative to how you think the potential of the Milky Way has evolved over time. And most excitingly for me, we were able to make a constraint on the age of the oldest disk stars. So this just shows a fit to a mixture model of all of those high alpha stars. So this red curve here, we were able to fit a mixture model using a hierarchical Bayesian modeling technique using PyFE3. And by combining all of the posteriors for the ages that we got for those high alpha stars, we were able to make a constraint of the age of that high alpha component. And we get an age of about 11.3 plus or minus 0.8 gigayear, with a spread consistent with being about 1.5 gigayears, which is extremely consistent with the results that we got from Kepler, and also with more recent works, for example, the work that Sam spoke about yesterday and the work by Josephine and Montalban. And I think by digging into this data set more, we'll be able to find really interesting stellar populations in the Milky Way. And so I think there's a real value in this kind of large but imprecise data set. And so you can go and use our catalog now. It's all there for people to use. If people are interested in getting the light curves from us, we're happy to share those, but I think there's better things available now probably. But the catalog of ages and Gaia parameters is all there, as well as luminosities and orbits for all the stars that we found in the CVZ. So, and you can scan this QR code if you want to get that. I'm kind of running out of time, so I'll just leave it with this, this summary and say that the TESS-CVZ provides great quality year-long light curves for bright giants, and probably more with extended TESS. And we were able to find a bunch of other cool results as well. And so I'll say thank you very much, and yeah, thank you.
Great, thanks Ted for a great talk. We are running a bit tight on the schedule, so if you guys have questions for Ted, please do use that Stellar Astrophysics channel to ask them, tag him in it so he sees it for sure. And I think we're going to move right on to the next talk, which is going to be Tansu Daylan, who's going to be talking about self-lensing black hole searches in TESS.
All right, thank you, Jennifer. Can everyone see the screen, I hope?
I can see and hear you, but I'm still seeing your presenter view.
Yes, so let me go full screen. Yeah. All right, thank you.
You're good.
Thank you. So yes, so this will be a slight change of gear actually to talk about compact objects, that stars, and especially in the context of a large search that I have been leading to find a special type of object, which I think could be very interesting if we can actually make a discovery of. And I'm working with many people on this project, especially my advisor, George Ricker, and also various people from the TESS team at MIT and at Yale and Goddard. So I'm a postdoc associate at TESS, as well as I recently started holding a visiting appointment at Princeton. So let's dive into it. Quick teaser would be that there's a lot of dead stars in our galaxy, and we kind of know this fact, but most of these black holes and neutron stars are actually observationally inaccessible to us. The types that we know currently are mostly X-ray bright, hence we know them through their X-ray emission, and more recently we know them through their merger by gravitational waves. But still, a large fraction of them are still escaping detection. And especially if you think about the mass function of black holes, we think that the lightest black holes must have a mass of order 5 solar masses. And if you take into account the evolution through mergers, we tend to think that the minimum mass should be around the same, but the upper gap that you may know, the gap beyond about 60 solar masses should be slightly filled due to mergers. So essentially the spherical cow picture of this black hole's mass function is that there should be a gap between neutron stars and black holes, so between maybe 2 and 5 solar masses, and roughly a power law distribution with some breaks here and there. So most of this is being probed by gravitational waves right now. But one thing about gravitational waves is that they probe sources very far away, not in our galactic neighborhood. So if you really would like to understand the dead star content of our own galaxy and try to relate this to our galactic archaeology, then we have to find much closer members, black holes and neutron stars. One observable we can use is microlensing, because these are compact objects. They can lens light sources behind. And especially in the context of having a stellar companion to these, you might imagine that these black holes and neutron stars can microlens light from a compact, from a main sequence companion. So, and this would definitely need treatment in finite source microlensing, because unlike the microlensing you might be familiar with from exoplanet detection, this is essentially a compact object just passing within the disk of a companion star. So the light curve that is, or the light curve features that are being produced are essentially a train of pulses that you can see here, or can be approximated to a good precision by a train of pulses, like you can see at the upper figure here. And you can, in this context, treat the compact object as essentially a light source that passes, transits the star periodically. So this adds a lot of information to our growing understanding, or at least would add a lot of information to our growing understanding of black holes. Especially it would provide precise mass measurements for nearby black holes, because those mass measurements that come from X-ray sources, X-ray binaries particularly, have a lot of systematics in them. And the mass measurement that you get from these are as good as your photometric precision almost. So you can really achieve good results if you can make a discovery. And this discovery would obviously be the closest black hole or neutron star to our solar system. So it would also be on a star that would be amenable to detailed characterization. So I like to call these objects compact objects with non-interacting stellar companions, or concerns for short. And I'll just give a quick introduction to what these look like in the test data, or should look like. But let me just make a quick note that a version of these objects that self-lens have actually been previously discovered. But that object actually is not a black hole, it's a white dwarf, and it's been discovered in Kepler data. In fact, there are more candidates that have been recovered even after that. And the reason why these discoveries have been constrained to white dwarfs is that black holes or compact objects, especially black holes with main sequence companions, we think are extremely rare. And only those white dwarfs at really long orbital periods have been accessible to Kepler, because essentially you want your Einstein radius to be larger than the physical size of the compact object, and that can only be true at large orbital periods. So as I said, the occurrence rate has to be really small. If you just pick up your black holes from the field, you tend to get occurrence rates of order once in a million or so for most masses and orbital periods of interest. And if you basically employ common envelope evolution, then your occurrence rate starts becoming an extremely sensitive function of orbital periods. So your occurrence rate is really pushed to lower orbital periods. And by putting upper limits on this, you would actually be able to learn something about whether or common envelope evolution is correct, or to what extent, and how we can actually modify it. So quick introduction. So a concern looks like the following in TESS light curve. It's got three components. It's got the ellipsoidal variation due to the tidal stretching of the main sequence companion. Then it's got Doppler relativistic beaming shown with green here. That is at the orbital frequency. So it's almost a cosine at the orbital frequency. The ellipsoidal variation is actually another sinusoid, but at twice the orbital frequency. And then self-lensing is, as I said, a train of pulses shown with red here that essentially happens once every orbit at the rise of the Doppler beaming component. And if you study the amplitude in units of parts per thousand as a function of orbital period, you can see that the self-lensing amplitude increases with orbital period, and the other two components decrease. So it's long orbital periods, you are more likely to find higher amplitude self-lensing signals, but then you get basically the penalty from the fact that your orbital period is getting close to your observation baseline, especially for TESS, so that is not a good thing. So now, as I said, if we go to smaller orbital periods, then the problem becomes that the signal is dominated by ellipsoidal variation and Doppler beaming, and not our self-lensing unique signature. So we have two strategies to search for these objects. First, in the TESS data, we generate features by detrending the light curve using a hybrid spline. And then we do inverted BLS, box least squares, and then we basically just trigger on the peaks. And then we look for consistency on the Lomskargel side. We again do the Lomskargel periodogram, and then look for peaks. If the peaks match, then we take it a candidate, and then we try to model it. The other component, the other line of research I won't have time to discuss, is an RNN that's trained on simulated data. And 3 students have been working with me on this project at various times, so I just wanted to mention them by name. Ram and Eli are looking into complementary searches for single transits, and Kartik has been doing testing and validation of the pipeline. And we have started first doing injection recovery tests on all cycle 1 and 2 targets with randomized black hole masses, periods, and transiting inclinations. So this is a real light curve, test light curve, and then we inject color-coded components to it to get the light curve that's now shown. So this is now a simulated light curve with the signatures that I just described. And then we first model it by using a detrending algorithm, spline fit, hybrid spline fit. And then we, as you can see in the detrended light curve down below, we can start seeing the pulses. Then we, on the undetrended light curve, we obviously look for LS periodogram features as well, look for the peaks, we detect them. On the BLS side, for the detrended light curve, we search for periodic pulses, then also tag them, and finally match those two. If they match, we call it a candidate, and this is an example, simulated example that actually passes our thresholds to be a candidate. And when we face fold, we get the pulse, and then if you zoom in, you actually see a nice pulse that's been detected. So we then confront the real data. So far, we have searched over the nominal mission data, as well as some cycle 3, selected cycle 3 targets that was submitted as part of a proposal for cycle 3. And out of all these, we have found about 5,000 positives, but none of these have survived scrutinized vetting so far yet. There are some candidates that I'm showing here. There are some single transits that we see, some moving object artifacts, as well as a lot of flares, flares that are just being phase matched to various random components in the light curve, as well as nearby eclipsing binaries and various things that do funny things in the background and then show up as pulses in your target light curve. So none of these have passed our thresholds. So then the natural question is it that there's no black hole out there? Or is it that our survey sensitivity is not there yet? And I think it might just be the second, the latter. So this basically motivates us to study our occurrence rate and precision, recall and precision to accurate levels, so that we can invert our non-detection into an occurrence rate upper limit. And so far, we have shown that our occurrence rate is at around 80% or so for most orbital periods and masses, for large ones as well, especially for large orbital periods and masses. And baking into the problem, the overall the transit probability, the overall recall is at about 2%. So essentially that means if it takes basically 40 relevant systems with signal for us to find one because of the recall inefficiencies as well as pipeline inefficiencies as well as the transit probability. So given that we have looked at around 200,000 light years or targets, that essentially tells us that the upper limit that we can currently put on the occurrence rate of these black holes for most masses and orbital periods is 1 in 5,000 stars, which is obviously interesting, but not enough for us to rule out interesting chunks of the phase space. So as the next step, we basically have an awarded cycle 4 proposal to go back and do this for all FFI light years down to a limiting magnitude of 13.5. That adds to about 10 million stars, and that's about 50 times more than what we have looked at. So we are really drilling down the occurrence rate plot to make sure that there's nothing missing. And we hope that by maintaining a similar recall, we will be able to use the 10-minute FFIs, which is very critical because we can actually look for these signals at lower mass stars, smaller stars. That's very important. And then we hope by the end of cycle 4 is to push our occurrence rate limit down to 1 in 100,000. And that will become interesting to rule out certain chunks of the phase space available to the formation of these objects. So with that, I'd like to conclude and take any questions. Thank you.
Great, thank you. We have a question from Avi, which is, have you found signals of heartbeat stars, which are eccentric binaries with a photometric tidal distortion signal at periastron?
Right. Yeah. So some of the binaries like heartbeats are coming into our catalogs as positives, but obviously false positives, because the most stringent, once you detect on the LS periodogram peaks, the most stringent cut is consistency, both amplitude and period wise with the BLS periodogram. And that pretty much kills everything. There are several kind of in the middle ground situations, but they're not 5 sigma detections. So they're just, I would say, still very tentative candidates.
Great, thanks. Okay, we're going to move on to our final talk this afternoon in this session, which is by Travis Metcalfe, and he's going to be talking about TESS, Asteroseismology, and LBT spectropolarimetry of an exoplanet host star. So take it away, Travis. I can see you, but I'm still seeing your presenter view. Maybe.
Yeah. Okay, and can you hear me?
I can hear you fine, but I think, yep, you're good now. Good to go.
Okay. All right, thanks. I'd like to thank the organizers for giving me the opportunity to talk to you today, and especially a big thanks to my amazing team of collaborators with a very wide-ranging variety of expertise that we brought together for this project. So somewhere around the middle of main sequence lifetimes, rotation and stellar activity appear to decouple. And this may actually kick in before the age of the sun, so it could be relevant to our understanding of our own solar system, in fact. So what I'd like to share with you today is the most direct evidence yet of what causes this change in the relationship between rotation and activity beyond middle age, and in particular that a shift in magnetic morphology is what's responsible. So the big picture here is that we are trying to bring together all of the measurements that are required to quantify the magnetic braking torque in sun-like stars, and effectively, equivalently, the rate of angular momentum loss. So that wind braking torque, following the formulation laid out by Finley and Matt in 2017 and 2018, it depends on the morphology of the magnetic field. So here parameterized by the polar strength of a dipole, a quadrupole, or an octopole field. So it's only the largest scale components that really matter. The mass loss rate, the rotation period, and then the global stellar properties, the mass and the radius. And so we get the rotation period and the mean activity level from archival HK, calcium H&K data from the Mount Wilson Observatory. We combine that with Asteroseismology from TESS to get the global properties, the mass, the radius, the age. We fold in measurements in the X-ray from Chandra, also with the ROSAT, to quantify the X-ray flux for our targets, from which you can estimate the mass loss rates. I'll show that a little bit later. And then finally, ground-based spectropolarimetry from the Large Binocular Telescope to either measure or set limits on the strength of these various large-scale components of the magnetic field. Okay. So the big picture here that was motivated by observations from the Mount Wilson Observatory of rotation and activity cycles in solar analogs. And in particular, this sequence of solar analogs, 18 SCO around 4 gigayears, Alpha Centae about 5.5, and 16 SIG around 7, seem to show that after standard spin down, where activity cycles are gradually getting longer as the rotation period slows, once stars hit a critical rotation rate for a given mass, rotation seems to stop evolving, and the activity cycle apparently grows longer and weaker until it disappears entirely in the case of 16 SIG. Now, looking at similar pairs of stars that have comparable rotation periods but are have different activity levels, we see similar kind of behavior in both hotter and cooler stars. And so our objective here is a first test of what might be different between a star that is clearly before the transition, like 88 Leo, and a star that is clearly after the transition, in this case, Rho Corbohr, which is our main target here. So we get the astroseismic properties from TESS. TESS observed Rho Corbohr in sectors 24 and 25 and allowed us to get a low signal to noise detection of solar-like oscillations. You can see an excess of power in the Fourier spectrum around 1800 microhertz. When we autocorrelate that range of frequencies there with itself, we get a peak that shows a characteristic frequency spacing that's similar to, in red there, that is similar to the predicted values based on the temperature and other properties of the star, shown as a blue line. And as additional check, we make an Echelle diagram of this region of the power spectrum to see where oscillation modes with the same geometry line up in ridges, vertical ridges here. And as a sanity check, we wanted to see that the ridge of dipole modes has a frequency offset that is consistent with what is expected from solar-like oscillations. And indeed it is. So we believe we have a secure detection of the global oscillation properties in this star. So we did grid-based modeling to get the radius, the mass, and the age. For 88 Leo, unfortunately, there was only one sector of observations in cycle 2. And so we were unable to get an astroseismic detection. So in the case of 88 Leo, we are estimating the radius from SED modeling. We use that with an empirical eclipsing binary mass radius relation to derive a mass. And then we get the age through gyrochronology from rotation, since it is before the critical rotation rate where rotation and activity decouple. Gyrochronology should provide a reliable age for that younger star. Okay. Now, to get the mass loss rate, mass loss rates are notoriously difficult to directly measure in stars. And so this plot from Brian Wood and collaborators just earlier this year shows essentially all the measurements of different types that can place limits on the mass loss rates. And fortunately, the mass loss rate appears to be correlated with the X-ray flux. And so you can use this correlation to predict for 88 Leo and for Rho Corbohr what is the mass loss rate that you expect given this empirical relation. And so we get a contrast between the two of a factor of 5. So the mass loss rate decreases by a factor of 5 between the age of 88 Leo, or between the flux of 88 Leo and the flux of Rho-Core-Bohr. Now, there is a lot of scatter in this empirical relation. The previous relation of Wood and collaborators in 2018 is a bit steeper, fit only to GK dwarfs. It's less scatter in that relation, but it's also applicable over a narrower range of X-ray fluxes. But fortunately, that range encompasses both 88 Leo and Rho-Core-Bohr. So if we use that alternative power law, you get this these estimates of the mass loss rate. And so that's a factor of 17 decrease. But to be more conservative, we adopted the smaller difference in mass loss rates for subsequent analysis. Okay. Oh, I should mention that the X-ray fluxes that we got here for Rho-Core-Bohr, we got a new measurement from Chandra of the X-ray flux, and we updated the old measurement from ROSAT of 88 Leo, considering the newly derived distance from Gaia and updated determination of its radius. Okay, so the Large Binocular Telescope gives us measurements and limits on the magnetic morphology. These observations were obtained in 2019. So this shows the degree of circular polarization across the line profile. And what you see is a signature of a dipole magnetic field in 88 Leo, a very clear detection. Keep in mind that we're looking at 1 part in 10,000 is the full scale here. So these are tiny degrees of polarization. It's hard. These are hard measurements to make. But for 88 Leo, we derive a dipole field with a strength around 5 Gauss. While for Rho-Core-Bohr, there's no significant detection, but we can use the little blip around the line center to set upper limits by assuming either dipole or quadrupole or octupole field. Now, we know the relative activity levels of these two stars based on their chromospheric long-term measurements of their chromospheric activity levels. And so we know Rho-Core-Bohr is 64% as active as 88 Leo. So if you just scaled down that 5 Gauss dipole field, you would expect to detect in Rho-Core-Bohr a 3.2 Gauss dipole field, if nothing else changed, for example, the geometry. In fact, we set an upper limit on the dipole field of 0.7 Gauss. If it's a quadrupole field, then you have patches of opposite polarity that cancel each other out. And so the amplitude of the field can be larger for a given line profile variation. And so the upper limit of a pure quadrupole field is 2.4 Gauss. That's still not at the 3.2 Gauss that we'd expect from the relative activity levels. If it's octupole field, there's plenty of room to squeeze an octupole field in there. And given these upper limits, we can say that the global field of Rho-Core-Bohr is likely to be dominated by quadrupole and higher order fields. Okay. All right. So what did we find when we put all of these things together? The first point is that the astroseismic age that we derive from TESS photometry for Rho-Core-Bohr is perfectly consistent with the mean activity level expected for that age from a sample of solar analogs. So in the background here is the activity age relation for a sample of solar analogs from Lorenzo Oliveira and collaborators in 2018. And you can see this is the gyro age for 88 Leo, the astroseismic age for Rho-Core-Bohr, and they fall reasonably close to that activity age relation. If instead you adopt the gyrochronology age for Rho-Core-Bohr, it's a significant outlier. So the astroseismic age is perfectly consistent while the gyro age is not. So with that as motivation, we tried to model the forward model the rotation period of Rho-Core-Bohr using either standard spin down, a standard spin down law, or weakened magnetic braking, where you essentially turn off magnetic braking around the middle of main sequence lifetimes. So for standard braking, you would expect Rho-Core-Bohr to have a rotation period around 50 days. with weakened braking, you can push that down below 30 days and just barely get to the observed period shown here in black. Now, this led us to suspect that the low signal to noise detection in our astroseismic study may be slightly biased. In fact, there is a bit of a tension between the observed, the astroseismic mass that we derived and the mass from isochrones and other analyses. If you use an alternate mass prior instead of the astroseismic mass, so based on, say, isochrones or the eclipsing binary relations, you can push that predicted rotation period with weakened magnetic braking down to be consistent with the observations. So by contrast with 88 Leo, standard spin down models can perfectly match the observed rotation rate as expected. So, but for Rocore Bohr, weakened braking models are required. So now we basically have all of the ingredients that we needed, as I showed in the beginning, to predict what is the magnetic braking torque for each of these stars and how do they compare. And so when you just plug in all of those ingredients, what we find is that the magnetic braking torque for Rocore Bohr is more than an order of magnitude smaller than it is for 88 Leo. And just to put that into context, there are a number of stellar properties that will naturally lead to a decrease in the magnetic braking torque. For example, the natural evolutionary decrease in the wind mass loss rate, right? And also the gradual slowing of rotation, maybe just by expansion on the main sequence if there's weakened magnetic braking, and also the gradual decline of the stellar activity level, the mean activity level. All of those things will produce a reduction in the magnetic braking torque. And so those expected things can account for a reduction of about a factor of 3 between the age of Rocore Bohr, or the age of 88 Leo and Rocore Bohr. To get that extra factor of 4 on top of that, that comes from the shift in magnetic morphology. So effectively, the elimination of the dipole magnetic field and the concentration of the field into smaller spatial scales like quadrupole and above. Okay, so we have new LBT spectropolarimetry for another 5 solar analogs that we expect to be able to apply the same methodology to in the near future. And we have 4 additional cooler targets planned. So we're planning to test this scenario across the full range of spectral types. TESS is going to observe in cycle 4 most of our targets in a 20-second cadence, and thanks to a DDT proposal for that in part. The one target that it will not observe that we're interested in is 18 SCO. That's a victim of the northward shift due to scattered light in cycle 2 and again in cycle 4. So I'm looking forward to cycle 6 to finally observe 18 SCO. But in the meantime, we have ground-based asteroseismology of 18 SCO. But with those 20-second observations, we expect we can improve the signal to noise for Rocore Bohr, the astroseismic detection, and hopefully get a detection, an astroseismic detection in 88 Leo to confirm this general picture. So I'll just leave up my summary of conclusions and encourage you to read the paper that was posted on Archive last night to get the full details. All right, and I'll take any questions.
Great, thank you, Travis. We have one question from Yutanatsu who says, do measured magnetic field values of these 2 stars have any info for discussing how morphology changed?
Well, basically, yeah. So effectively, the younger star, 88 Leo, is totally dominated by a dipole field, which makes sense from everything else that we know about it. Whereas the dipole field in Rocore Bohr is much less, it's much weaker than you'd expect given its relative activity level. The best model that we have, if you want to try to satisfy both those constraints at the same time with a mixture of dipole, quadrupole, and octupole fields, we find essentially no dipole field in Rocore Bohr, mostly quadrupole field and some octupole field to account for the total relative activity level. And the breaking torque for that model is 6% as strong as the one for 88 Leo. So these are snapshot observations in spectropolarimetry. We're not covering the full rotational phases. And so that's an area where we could improve in the future to get full Zeeman Doppler mapped, for example, for 88 Leo. I think it's for a non-detection, it's kind of hard to convince TACS to let us get non-detections over and over all the rotation phases. But that's the state that we have right now, and data like these for 5 additional solar analogs that will be analyzed soon.
Great, thanks, Travis. We are over time, so I'm going to ask everybody who has further questions for Travis to take advantage of that channel on Slack. This is the last talk for today, so the conference picks up. There's no announcements from the organizers or anything. Conference picks up at 1 p.m. UTC time tomorrow, whether that's morning, noon, or night for you. Thanks everybody for coming, and thank you all to the speakers today for excellent talks, and catch you all tomorrow.
Thank you, Jennifer. Thanks.